Devo fare...
Ok. Allora, aspetta, devo riuscire. No. Sì, devo riuscire.
Forse devo uscire di nuovo adesso.
Poi ancora non me lo fa fare, vedi? Perché? Ma secondo mai questa cosa?
Aspetta, quando sei uscito.
Ok.
Prova qua. Torna.
So, good morning, everybody. It's a pleasure to have here today Stefania Salvadori. Stefania graduated at the University of Florence. Then she moved to Trieste, where she got her PhD in 2009 in CISA, under the supervision of Professor Andrea Ferrara. And then she won an independent fellowship, the Nova Fellowship, and she moved to Groningen. And she worked in collaboration with the Link Tolstoy and their team. Then she won another independent fellowship, the Lenin Fellowship. So she spent 6 years in Groningen. Then she moved to Paris Observatoire, working with Piercarlo Bonifacio, again in the field of first stars and especially the chemical composition of the first stars. And then finally, she moved to Florence, where she's associate professor now, and she also won a ERC grant, the NEFERTITI project. And of course, she will be talking about first stars and their properties today. So I leave you the floor.
Thanks a lot, Donatella. It's really a pleasure to be here. So really, thanks for the introduction and for the invitation. It's good to see a lot of faces, also old faces that are here. I didn't expect that. So today I will talk about the chemical fingerprints of the first stars. So let me just start to introduce, especially for the students that perhaps are around, why do we care about the first stars? Oh no, sorry, I should move this one again. So meanwhile, I can talk. Okay. Hide. Okay. Okay. So we expect that the first stars have formed some 100 million years after the Big Bang, when the universe was extremely simple, essentially made only by neutral hydrogen and helium gas. So when the first stars formed, they actually provided the first sources of photons that started the ionization process, and they also synthesized new chemical elements that were then released into the surrounding gas, thanks to the first supernova explosions. So it is clear that the first stars had a large impact on the formation of the first galaxies, and if you want, also settle the initial condition for the formation of all the galaxies that we observe today, including our own Milky Way. And the key point is that how many metals are produced, the amount of photons produced, the kind, and the amount of heavy elements produced depends on the properties of the first stars, and in particular their mass. And this is why we are so interested in understanding that. Now, what do we know? Where did the first stars form? Now, if you believe in the standard lambda-Kodak models, then these first stars should have appeared in the first virarized structures that are called the first mini halos. And these objects have a zero temperature that is lower than 10 to the 4. So in the primordial composition gas, the only available coolant is molecular hydrogen in this condition. And just to give you some numbers, these mini halos are expected to have masses, total masses of the order 10 to the 6, 10 to the 7 solar, a redshift around 20 or 30. So they are very, very small objects. Now, what do we know about the properties of the first stars, the mass in particular? Not so much, but there are actually very strong physical arguments that are suggesting that the first stars were most likely more massive than those that we observe today. And these essentially are the results of the fact that these first stars form from a primordial composition environment with no dust and no metals. And the argument is the following. So what you have when there are no heavy elements is that you can only cool down your gas through molecular hydrogen, which is a poor coolant. So it depends really on the microphysics of the molecular hydrogen, the fact that you start to cool down the gas inside these halos, the gas cools and fragments. And then what you reach is a state in which you have the typical mass of the so-called protostellar gas clouds, which is of the order of 1,000 solar. And the temperature in this protostellar gas cloud is of the order of 200 Kelvin. And the temperature is very important because it's more than an order of magnitude different with respect to what we do observe today in local star-forming regions, where, of course, the metal cooling and dust play a fundamental role to have more fragmentation and more efficient cooling. So this is the key point. So we see that in primordial star-forming regions, we have very large protostellar gas clouds, while in present-day star-forming regions, these protostellar gas clouds have masses that are of the order of 1 solar. Okay, and this is the first. Then from this protostellar gas cloud, you will form in the center a protostar, and then you will start to accrete the gas, and then you will finally have your final first stars. And the point is that also the accretion rate of this gas into the protostar depends on the temperature of this gas. So again, the accretion rate is much larger, is higher in primordial composition. Now, these two ingredients together let us, let's say, suggest us that the first star should have been more massive than those that we observe today. And this is not only the only difference, but also we do expect them to form in isolation. So just 1, 2 stars per mini halos, while in local star-forming regions, we have a lot of fragments and we form stars in stellar clusters. So this is the big difference. But okay, we know this, but we don't know at all what was the mass distribution, which you prefer the initial mass function of the first stars. Is totally unknown. So this is displayed in this sketch here. So on the left, you have the first stars, which are also called population tree stars. And on the right, you have present day. So the present day stars, we can measure the mass distribution, which has a characteristic mass of 0.35. And those of the first stars, we don't know. Probably the characteristic mass is of the order of 10, 20 solar. But we don't know what was the shape. And this is what we are interested in. So in this talk, I will really try to address this question. So I will try to see how can we actually prove the mass distribution of the first stars, and if very massive first stars, which are predicted from hydrodynamical numerical simulation, really formed, and also if we can also form long-living low-mass stars in the very early universe. Now, it is very difficult to study the first stars because of 2 main reasons. First of all, if they were very massive, then you know that stars with masses larger than 10 solar disappear in some tens of mega years, exploding a supernova. So this means that the first stars rapidly disappear. And then we are talking about objects that are located in the very early universe, 13.5 billion years from now. So this is the problem. So not even the superb eyes of JWST will probably be able to detect the light for the very first stars hosted by the poorly star-forming mini halos, just because they are too faint and far away, okay? So we need to study them in a different way, in an indirect way. And we can do that. And we actually exploit the fact that the first stars, most of them, will explode as first supernovae, so enriching the surrounding gas with their chemical products. So what I'm showing here is an old figure, which is still valid from a paper from Hager and Woods in 2002, so 20 years ago, which is showing the final mass of the first stars with respect to the initial mass. So the remnant with respect to the initial mass. In the color regions, you can see what are the mass ranges in which you expect to have a strong contribution to the metal pollution because of supernova explosions. So you have 2 ranges. At very high masses, you can see that there is a very specific range from 140 to 260, where you can have the so-called pair instability supernovae. So what you have in this case is that these stars explode with a very high energy, up to 100 times the energy of normal core collapse supernovae, and they can totally disrupt the stellar progenitor. So there is no remnants. And because of this, you essentially inject into the surrounding gas 50% of the mass of the stars in the form of very elements. So they're really strong pollutants. On the other hand, you also have massive first stars from 10 to 100 solar, which can explode as supernovae, providing 1% of their mass in the form of heavy elements. And in this case, you can have a range, a variety of possible explosion energies, from the faint supernovae up to the so-called hypernovae, with an energy which is 10 times the one of core collapse. Now, here we have the key point. So if this first supernova explode and reach the medium, then what we do expect is that at a given point, the interstellar medium will be polluted up to a critical metallicity value, which will allow them to have an efficient cooling and fragmentation, and then will drive the formation of the stars from a massive star formation mode to the normal one that we do observe today. Now, this critical metallicity is still uncertain, but it should be between 10 to the minus 5 plus or minus 1. Okay, so when this happens, we have done our job, because if we form normal stars, it means that there will also be low mass stars with masses lower than 10.8 solar, which have lifetimes that are longer than the age of the universe, and therefore that can survive until the present day. So we can observe them in the surrounding Milky Way or nearby dwarf galaxies and study their chemical properties. So this is essentially the main idea behind the near-field cosmology, or if you prefer, stellar archaeology. So the idea is to study the properties of local ancient stars, metal poor. You want to go at the lowest metallicity because you want to really find those imprinted by the first stars. And we expect these stars to preserve in their photosphere the environment of formation, which is providing us indirect information about the properties of the first supernovae. Okay, so it's a long journey, but still we can make it. And in this way, we have a direct window, which is allowing us to really explore very early times through the local fossils. And of course, we can also exploit all the surveys that are available and that will be available soon. Now, as I said, it's a long journey. And in order to make this job, we really need a tight synergy between observations and theory, because you need observation to find the stars, the theory to interpret, but also to, as I will show, predict which are the best candidates to be followed up. And this is essentially the key idea behind the ERC project NEFERTITI, that is a stand for Near Field Cosmology with Tracing Invisible Time. And you can see in this logo, which has been designed by one of my PhD students, Martina Rossi, that we really have this the theory and observation that are really tight and working together hand by hand. So here I just want to give you a flash of some of the faces, the people that are actually contributing to the work I will show today, and that are part of this NEFERTITI team. So let me start by showing some observations of present-day ancient stars. Now, the ancient metal-poor stars are typically identified in the galactic halo of our galaxy. This has been the best studied environment, because this is one of the most metal-poor. And what I'm showing here is actually the metallicity distribution function, so number of stars with respect to the iron abundance, which is a metallicity indicator, for a very large sample of stars, 140,000 in the galactic halo, derived from the Slow Digital Sky Survey. So this is, let's say, an attempt to have an unbiased view of the metallicity distribution function. So as you can see, there are not so many stars that are very metal poor. So the majority of the stars, even in the galactic halo, appear at iron abundance of the order of -1 or even higher. But what we want to do is really to study the very metal poor stars, which are those which have an iron abundance that is lower than 1% solar. And these stars, you can immediately see that are very rare, less than 1% of the total. Okay, so observers are doing a great job in finding these rare objects. Now, the key point is that they've been working from, I think, since 2 or 3 decades in finding the most metal poor stars. And those that have the lowest iron abundance have actually been followed up at higher medium resolution, so we can have a lot of information about the different chemical elements that have been observed in the stars. And here I give you one example. So I now just focus on these very metal poor stars. And what I'm showing is the carbon over iron abundance with respect to the iron for the sample of very metal poor stars observed in the galactic halo. This is just a compilation. The data are not from myself. Now, you can see that there is a line which actually separates the stars into 2 groups, the so-called carbon-enhanced metal poor stars, which have a carbon over iron abundance that is larger than 0.7, and the carbon normal one. And among these carbon-enhanced metal poor stars, there are also 2 different groups. The one that are shown there in gray, as gray dots, that are the so-called CMPS or CMPRS stars. And these stars not only have a carbon excess, but also have an excess of barium. And barium is a slow neutron process capture element, which is produced by AGT stars. So the key point is that these CMP stars have been followed up, and it has been found that they reside in binary systems. So it is believed that the carbon and the barium excess in these stars is not representative of the environment of formation, but has been acquired through the binary companion that pass the IGD phase. Okay, so they are not interesting for our purpose. On the other hand, there are the so-called CMP stars that are the black dots there, which are not preferentially found in binary systems, and they don't have a barium excess. So it is now been, I think, established that these CMP stars, the chemical abundance we observe in the photosphere is really representative of the natal cloud in which they form. And as you can observe, these stars become more frequent as you go towards lower iron abundance. And this can suggest a link with the first stars. And indeed, these CMP stars are believed to be directly connected with the very first stellar generation. Now, another important part of the puzzle is the fact that these carbon-enhanced metal poor stars, CMP, have been also observed in ultra-faint dwarf galaxies. And ultra-faint dwarf galaxies are fantastic galaxies because they are among the most metal poor and ancient galaxies which you observe. And essentially, they are dominated by a very old stellar population. And many authors, including myself and Donatella, established that the first stars must have been hosted by these ultra-faint dwarf galaxies. So once again, there is a link with the first stars. Now, this is the situation. Let's try now to understand what these CMP stars are. And let me start with something that is absolutely simple, general and simple parametric study. Okay, let's start from the simplest one. So what we want to do is to investigate what are the chemical properties of an interstellar medium which has been predominantly imprinted by POP3 stars. So where the metals for POP3 stars, the first stars, provided more than 50% of the total. And then we also account for the imprint of normal POP2 stars, which can start to form earlier. Okay, so essentially what you need to do is to take into account for their knowns related to early cosmic star formation. And essentially there are three parameters in this model. The first one is the mass of gas which is converted into stars, so the star formation efficiency. The second one is the mass of gas into which metals are effectively diluted, which is encapsulated in this dilution factor, and here we have a sketch. And the third one is the mass fraction of metals coming from POP3 stars. Just these three, okay? And now I don't want to bother you with the equation, but with these just three parameters, then you can derive analytically some equations which allow you to study the metallicity and the chemical abundance ratios of all the different elements in an ISM which has been imprinted predominantly by POP3 stars. And what I want to put out here is that essentially the chemical abundance pattern only depends on this beta which is, let's say, a parameter which is related to the fraction of nodules provided by POP3 stars. So it's very simple, okay? Now, the only answer, the hypothesis we are making here is that we assume that to form one star per million, and this is driven by, let's say, the results of hydrodynamical simulation, and this is because we want to understand, okay? Now, this is a model that I developed together with Carlo and other collaborators, and the aim was to study the per-instability supernovae, and I will come back to this later. But during the last year, with one of my PhD students, Irene Vanni, we explored and we made it more general to also investigate the properties of massive first stars from 10 to 100 solar. And not only investigate the different masses, but the different explosion energies. So we will now concentrate on that. And let's see what this very simple model that we can easily understand is telling us about these CMP no stars. So these are the results of the model. In the top panel, you can see the result for low energy supernovae, so faint and core collapse, and in the bottom one for high energy and hypernovae. The dots here are the observations, and the colored area represents the results of the model. So high probability is when you have the violet colors. So what you can immediately say is that you actually need low energy POP3 supernovae in order to populate the region above carbon over iron larger than 2, okay? So this is really telling us that CMP no stars form really in environment which have been polluted by primordial low energy supernovae. Now we can ask ourselves, okay, how does this picture change if we also include the contribution of POP2 stars, which I said the normal POP2 stars, which explode at core collapse, which can start to form early on. And the results are here. So these are exactly the same, low energy and high energy, but in this case, the colors show an ISM which has been only imprinted by population 3 stars, the yellow, and then the contribution from population 3 stars decreases down to 50%, which is the violet one. And what you can clearly see is that the highly carbon enhanced CMP no stars with carbon over iron larger than 2, they only stay into the part of the region in which you have 100% imprint by POP3 stars. So these are truly second generation objects, stars which form from an environment only enriched by the first POP3 stars exploding as low energy supernovae. On the other hand, the lower is the carbon over iron, the more, the higher is the probability to have a star that is also contaminated by the chemical products of normal population 2 stars. Now, so we have a general results, but perhaps the model is too simple. Many of you perhaps may say, okay, that is just a parametric study. So let's try to increase the complexity. And for example, let's have a look at what happened in ultra-faint dwarf galaxies by using this approach, which has been developed by another PhD student, Martina Rossi, who studied the properties of ultra-faint dwarf galaxies, and in particular, in the evolution, in particular focusing in the best study one, that is Mutis 1. And the, let's say, the idea is that we assume that these ultra-faint dwarf galaxies are associated to the first primordial mini-halos, and this is supported by cosmological simulation. And we assume that they are evolving in isolation, and this is supported by the star formation history. So in this case, you also have pre-parameters because we'll always have in theoretical models, but the star formation efficiency and the supernova fielding efficiency here are calibrated in order to reproduce the global properties of Mutis 1, which is the red dot there, okay? And you also reproduce very well the metallicity distribution function. Now, the model is more sophisticated, and it also taken into account the incomplete sampling of the mass distribution, which is extremely important in poorly star-forming systems such as ultra-faint dwarf galaxies. This is a video showing that. So on the left, you can see the star formation rate during the first burst. And on the right, you can see how the theoretical mass distribution, which is the red, is populated with respect to the effective one. And in this case, note that we are assuming the same mass distribution also for POP3 stars. And you can see not even at the peak, you can actually populate all of it. So this means that you are missing some supernovae, Okay, so it's very important. And clearly, when we take into account the fact that POC3 stars can have also a different mass distribution, this is for characteristic mass 1, 10, or a flux, you can see that you really populate very badly the ISM. So this model takes into account all of these ingredients. And these are the predictions of the models for the chemical abundance of all the different elements, and they are compared with the observation of stars in Bootes 1. And essentially, these results are very well reproduced and are independent of the POC3 AMF, just because the bulk of the stars in Bootes has been formed by normal population 2 stars. But what we found, you can see there that there are also here these carbon-enhanced stars. So we can ask ourselves, where do they originate? Okay, so we can make the same experiment as before and separate the contribution from the different kind of supernovae with different explosion energies. So here, the yellow are faint supernovae, the red core collapse, and the violet hypernovae. And as you can see, also here, so this is all the, let's say, the area covered by the models, you can see that the most extreme values are only achieved if you include the chemical products of low energy supernovae. So it's consistent with the other case. And also in this case, to explain the existence of these 2 stars in Bootes 1, which are not so enhanced in carbon, we need to have this low energy POC3 supernovae. So they are consistent. Now, it's still too simplistic, the model. It may be we have a galaxy in isolation, so we can again increase the complexity and take look at antibody simulation plus any analytical models. So we take a Milky Way analog and we follow consistently the star formation and the chemical evolution along the formation of the galaxy. Okay, and also here we include the incomplete sampling of the POC3 AMF and so far and so forth. So also in this case, we have 3 parameters, but since we have a lot of observation for the Milky Way, they can be fixed by reproducing the final gas and stellar mass and the final metallicity of this population. And also we should be able to reproduce the metallicity distribution function for stars in the galactic universe. So this is at the high F-H end, and this is at the lowest F-H. Here we collect all the data from the SAGA database, and these are just upper limits because here the observations are very biased, so we should take into account this. And so we can ask ourselves, okay, what about this carbon over iron? And this is what we found. So these are all the stars together in simulation, so both halo, bulge, etc. And what you can see here, the color are showing the minimum contribution from low energy POC3 supernovae in each pixel. So you can clearly see that all the carbon enhanced metal pool stars, or at least all that are above 1, are actually dominated by the chemical products of POC3 supernovae. And those that are at the very high end of the carbon over iron are again at least 80% polluted by the first stars. So I think we can, let's say, we can now be convinced by the fact that these carbon enhanced CMP stars are really imprinted by massive first stars with masses between 10 and 100 solar, exploding as low energy supernovae. And in particular, that the most iron poor and carbon enhanced are probably truly second generation stars. Now, this is very interesting because we are starting to probe a mass range for the first stars. But in this picture, you can see we just probe the intermediate mass stars. So what about stars that are smaller or that are bigger? So let me first concentrate on the high mass end. So in the picture I showed you before from Hegel and Moseley, I show you that very massive stars can explode as energetic per-instability supernovae. And these per-instability supernovae and the signature of them have been searched for since decades, and no clear evidence of this signature have been found so far. And here I'm showing, so it's again the same model I was mentioning before, an ISM, the chemical abundance of an ISM, which is imprinted by per-instability supernovae with different mass. So from 150 to 206, the colors are showing this. Only per-instability, 100%. Now you can see that it's a mess, okay? You cannot find any chance. But you can notice that in all the models, you have a very strong odd-even effect. That is what the observers have been looking for since decades. Now, when I was in Paris with Carla, I was really puzzled and say, okay, but this should exist because hydrodynamical cosmological simulation, we found that this should be there. So otherwise there is something wrong. So we were really trying to find a strategy to select this candidate. And then by looking to this plot, which is a mess, you can, however, see that in the gray area, there are some elements that you can see that are not produced by all the models independent of the mass, and in particular zinc and copper. Okay, there are also nitrogen and fluorine, but let's skip that. Okay, so, and the point I then explore again with Irene is that if you again look at all the possible POP3 stars and supernovae, what you find is the zinc over iron that is very low can only be accounted for these parents and supernovae that do not produce zinc and copper, or very small amounts with respect to all the other ones. Okay, so this is really a peculiarity of an ISM imprinted by these very massive stars. Now, the question we posed to ourselves was, okay, this is something, but then what happened when POP2 stars start to contribute to the chemical enrichment? Are they just washing out this wonderful chemical signature? And this is why I developed the module. So here you can see, it's a bit weird, but by the way, here you can see the results. So for an ISM imprinted by per instability at a 90% and a 50% level. And the rest is done by normal POP2. And what you can see, let's focus on this one, is that if the per instability contributes by at least 50%, you should have a low zinc over iron, lower than subsolar, the solar value. Sorry. Okay, so it means that this lack of these chemical abundance ratios is preserved, and that's why we call them the killing elements to find very massive stars. So now we have a strategy because we can look for candidates that are zinc and copper poor with respect to iron. And this is what we did. We look at the literature data and we found a stars that is consistent for being imprinted by per instability at a 50% level. Still, is not super convincing. It's similar to the Aoki star. So we want to do better. But the problem is that there are not so many measurements of zinc. So we are pushing WEAVE to have the green gratings and to have zinc. But meanwhile, we should do something else. So with David Aguado, actually, this was his own idea, we decided to do something different. So to exploit all the available elements and the full chemical abundance ratios predicted by the models in order to find candidates from all the available surveys. And we developed what we call the PISM Explorer. So the idea is that we start from the theoretical prediction of the model, and we produce, let's say, a grid of models for different free parameters, and then we give them to the FERRE code, which is able to analyze a large amount of data from different surveys and to interpolate among the grids, and then to find the models that best reproduce the available chemical abundance pattern. In some cases, we have just 5 elements, which is the minimum required. And then we have a candidate, and then the candidate is inspected in full more details to be sure. And so this is how it's working. It's just a video showing an example of this, and then FERRE is really trying to interpolate. So the points here are the observations for one of the stars, and then FERRE is really finding different solutions, and then it's finding the best one. So it's providing us the predicted level of enrichment for POP2 stars and the mass of the per instability and the chi-square, of course. So I'm really happy about this Spin Explorer. I think it has been a wonderful idea. And David actually explored let's say more than 1 million stars available in Apogee, Gala, Gaia ISO, and also the GINA database. So what we are showing here is the metallicity distribution function in blue of all the candidates in explored, and in red, okay, this is normalized to let it visible. There are the 164 candidates that we found. Now we are we applied, and we are applying for time to obtain the full chemical abundance of this, because then it would be great. So what I'm particularly impressed is the fact that Ferre is just using the chemical abundance ratio. So I'm not giving any information about the iron abundance predicted by the models, but you can see that the peak of the metallicity distribution function of our candidates naturally has roughly the same value that we found in the models and also in cosmological models. So this is, I think, impressive, and let's say I think we are going in the right direction. This is telling me that there should be something good into this sample. Now, I think I still have 10 minutes, is correct, roughly, or less, 10 minutes, perfect. Okay, so I also have the time to go then to talk about the low mass end, okay, that is the other part. So the intermediate mass we prove with CMP no stars. In the high mass now we have a strategy to find the business angles. What about the low mass end? Now, the key point here is that if you are able to form low mass stars in the early universe from primordial composition gas, then those that have a mass that is lower than 0.8 should survive until the present day, okay? Then we should be able to find them and to detect zero metallicity stars. Once again, this is something that the observer has tried to find since decades. I think it is the dream of any observer. And so far, no zero metallicity stars have been found. So there have been several people listed there, and the list is not exhaustive, that try to use this persisting non-detection of zero metallicity stars to infer something about the minimum mass of the first stars. And actually, Hartwig pointed out that in order to constrain the minimum mass of the first stars at a given confidence level, we should actually tell what is the sample size, so the total number of stars that we should observe. So he made this calculation for the halo and for the bulge, and for the halo find something like 10 to the 6.5 or larger. Okay, so large number. Now we are approaching them, but we are still far away. So with Martina Rossi, we decided to focus them on ultra-faint dwarf galaxies. Let's make the same experiment with ultra-faint dwarf galaxies, which are the oldest and the most metal-poor object. So the model is the one that was presented before for Bootis 1. And what we did was to actually assume a given mass distribution for the first stars. In this case, I'm showing, let's say, a normal one, like the one that we observed today. And we were varying the minimum mass, and also then the characteristic mass, the shape of the mass distribution. And then we were counting in our final Bootis the fraction of zero metallicity stars with respect to the total. So if you have a normal initial mass function, like the one that we observed today, with a minimum mass of 0.1, you should expect 12% of zero metallicity stars in Bootis. So we observe 44 stars, we should have already found at least one, even more than one. So we made this experiment for different characteristic mass, and then we quantify the required sample size in order to constrain the minimum mass at a given confidence level. And what we did, and this was an innovation with respect to the other work, was also to compute the synthetic or magnitude diagram first, because we should, let's say, quantify the sample size that we can actually observe with current facilities, okay? So the current limit in magnitude is of the order of 19. So we did this experiment, and what we found for the case of a characteristic mass of 35, that is normal mass distribution, and 1, is that by using the sample, let's say this is the required sample size in order to constrain the minimum mass of 0.1, 0.5, and 0.8. And the curves show the 68 confidence level and 95 and 99%, okay? So in order to constrain at a 99% confidence level, you need a sample size that is larger than 80. So we don't still have this. But then we said, okay, but our models that are those in the blue area are also good in reproducing the properties, the global properties of other ultra-faint dwarf galaxies, such as Leo 4, Hercules, Eridanus 2. And if we take into account also the total number of stars that we observe in them, then the number is 100. So we can say, and then we clearly investigate the properties and the NDF, and they are all consistent. So by using this joint probability, we can now say that we can already constrain at a 99% confidence level that the minimum mass of the first star should be larger than 0.8, or that the characteristic mass should be larger than 1. So you can see, thanks to theory, this is why theory and observation should be linked, because you can even exploit the non-detection of something to put some limits on the mass distribution. And then clearly with the ELT, we can do it much better, because we will increase, let's say, we can go deeper up to 25 in magnitude and then increase the sample size. Essentially, we can observe all of them in this ultra-faint galaxy. So we can constrain even a characteristic mass of 5. So in conclusion, I hope I convinced you that near-field cosmology, or if you prefer stellar archaeology, is a powerful tool to study the first star's mass distribution. So I've shown that CMP stars are most likely the descendants of first stars with masses between 10 and 100 that exploded as low energy supernovae. And in particular, those with high carbon abundance are truly second generation stars. Then I show you that we now have tools to identify the missing descendants of pearl instability supernovae, and that's to probe the high mass end of the metallicity distribution function through the PINS Explorer. And let's hope to have time to observe these stars. And for the low metallicity end, instead, we can exploit the current non-detection of zero metallicity stars in ultra-faint dwarf galaxies. Now, in the last 4 minutes, I just show you a last slide because, okay, so we are really starting to probe the mass distribution. Now I'm middle of my year C. I really hope in 2.5 years to come back really with some shape as well. But as I showed you before, this is not the only story, because we also have an energy distribution function for stars that are masses between 10 and 100. So far we only proved the low energy supernovae. So what about high energy supernovae, in particular hypernovae? So it's just a flash on this paper that has been led by Ausa Skuladottir, an RTDA in the University of Florence, that she actually discovered the most iron poor star in the Sculptor Dwarf galaxy. That is the red point here. And as you can see, this star is quite peculiar. Here is showing the magnesium over carbon calcium abundance with respect to iron. And you can see that it's underabundant with respect to the stars in Sculptor, that are the blue dots, and in the galactic halo, the gray, and in ultra-faint dwarf galaxies. So we analyzed in detail this star, and then we tried to fit the chemical abundance pattern with different models, including the faint supernovae, including the pearl instability, including a normal pattern typical for normal carbon stars like the one in the chiral sample. And at the end, so we ran 13,000 different theoretical models, and we found that the best solution was an hypernova of 20 solar mass. So this has been published, and of course, Ausa is now the leader of the 4 dwarfs surveys for MOST. So in the upcoming years, perhaps we'll find more of these objects. And I stop, and thank you for the attention.
Okay. Do you have questions? Tyler?
Yes.